大家好，我是清华大学电机系黄远介。In the last three lectures, we just finished up our discussion on transmission line. And if you still remember, the signals on the transmission line are voltage and current. And voltage and current are scalars. So the calculation is relatively simple. For example, if you add 2 volts with 3 volts, then you end up having 5 volts. But now we want to talk about electric field and magnetic field in the wave. And those fields are vectors. And starting this lecture 5, I'm going to talk about electromagnetic wave. And you have to consider the amplitude of it together with the directions of the field. So the mathematics is going to be expected more complicated, but you don't need to worry too much about it because in this lecture I will do a lot of review and repeat a few things that I have told you before. So in this session 5.1, I will just do some review and also introduce you the basic concept of an electromagnetic wave. And we'll be again talking about sinusoidal signals. For this wave, it's going to be a time harmonic plane wave. And I will show you some geometric constructions for a plane wave so that you can remember the concept more deeply. And then I will talk about the ratio between the electric field and magnetic field for a wave. And this is called wave impedance. And finally, I will do some review. So the first topic is the electromagnetic wave. And apparently, the electric field and magnetic field are coupled together in a wave. And we want to look for the origin of this concept. And if you look back lecture 17 in electromagnetic 1, then you can dig out this Faraday's induction law, and this will connect the electric field to magnetic field. And we talk about electric generator. If you have a magnetic flux density changing over time through this circuit loop, then you will induce the electric field on this loop. So this is the first evidence that a magnetic field is connected to the electric field, except that the time variable has to be introduced in this expression. And then we also talk about Ampere's law in this lecture. And we say that if we do a temporal derivative of d, then this term is going to be equivalent to a physical current. And we prove it from this circuit. And this current is called displacement current. So this is the second connection between electric field and magnetic field. And the key is that the electric field and magnetic field must vary with time. And so we can continue to look into this time-varying field by having some time-varying source in space. And this is given in the last lecture of electromagnetic 1. Suppose we have some time-varying current and also the charge in space here. And we say that after some time, you can detect vector potential or scalar potential in space a distance r from the source. And suppose the source is oscillating with time, denoted by this temporal variable of time t prime. And you put a detector here. And after some time, you will detect the signal. And the delay of the signal is due to a finite propagation speed of this radiation produced by this source. And this speed is calculated to be equal to 1 divided by square root of mu epsilon. Mu is the permeability of the space, and epsilon is the permittivity of the space. In vacuum, this mu and epsilon are still finite, and if you use the vacuum values to calculate this expression, then we call this the vacuum speed of the radiation. And then we now know that the electromagnetic energy can propagate in space as a wave over some distance with a finite speed. So in lecture 18 of the electromagnetic 1, and also in the first 2 lectures of the electromagnetic 2, I introduced you the wave equations for electric field. And the electric field and magnetic field are coupled together, and the magnetic field also propagates as a wave. So it also follows the wave equation for its propagation. And in this expression, the general solution will have this form, but the amplitude now is a vector field. It's not a scalar field. There's the magnitude and also direction associated with this amplitude. And if you write down the general solution for the magnetic field, you also have a vector amplitude in front of this general solution. And I highlight this general solution here because I want you to pay attention to this argument. And if you still remember when we introduced this general form, I told you that this t is the time variable and r is the position of your interest, and u is the propagation speed of the wave. And the plus sign and minus sign here are related to the propagation direction of the wave. For example, if you pick up this minus sign in your expression, then this means that the wave will be propagating along the positive r direction. And of course, if you choose the plus sign in this expression, then the wave is going to propagate in the backward direction along the minus r direction. And the speed of propagation again follows this expression. And a sinusoidal signal is particularly useful because it's easy to analyze, and also Fourier transform will allow you to use the sinusoidal signal to synthesize any arbitrary waveform. So as a wave, as an electromagnetic wave, we also look into so-called time harmonic field, for which the signal vary sinusoidally with time and also position. And if you have a time harmonic field, then you can express the signal like this, and just take the real part of it, of this complex expression, then you have the real signal. And this psi here, in general, is a function of position r, because the wave will propagate over some distance. So for sure that the signal will be a function of time and also the position. But for the temporal variable, it just tells you that the signal, the field, will change over time and having a sinusoidal variation. And if you have a harmonic field, then you can adopt the phasor notation. So the phasor notation, the phasor of a harmonic field is that you write into this expression and just leave out the exponential j omega t from the expression and pick up this complex amplitude. Then this is defined to be the phasor of the harmonic signal. And once you have the harmonic signal, then you could just drop the temporal dependence in your analysis, because previously in the last lecture of the electromagnetic 1 and also the lecture 1.3 of electromagnetic 2, I already told you that you can just keep the position part of your phasor and just take out this exponential j omega t and then put this expression into the wave equation to have this Helmholtz equation. So in this Helmholtz equation, you only have the phasor, and you don't have any temporal variable. So this analysis will be simplified. Now you can just focus on the analysis related to your coordinates, but not related to the time variable. And in this expression, there's a parameter called k, which is the wave number of this wave. And this k is equal to 2 pi over wavelength. And if you just put this into the wave equation, you're going to see that this k is equal to the angular frequency divided by the speed of the radiation. And the connection between electric field and magnetic field can also be converted into phasor notation. You just replace this temporal derivative with j omega, and then replace those variables into the variables with phasor notation. Then for the Faraday's law, you can write it into this phasor notation like this. And this is going to be useful when we talk about the ratio between electric field and magnetic field in the final part of this lecture. And you can also do the same thing to the Ampere's law. So the in phasor notation, the Ampere's law is going to be like this. And again, you replace this partial derivative of t with this j omega, and then put those variables into their phasor form. Then you get the phasor form of the Ampere's law. So in this session, I talk about a time-varying magnetic field will generate a time-varying electric field. Or if you have a time-varying electric field, you also generate a time-varying magnetic field. So electric field and magnetic field are coupled together if you introduce the temporal variation to the two physical quantities. And this time-varying field will propagate in space with a speed equal to 1 over square root of mu epsilon. And mu is the permeability of the medium, and epsilon is the permittivity of the medium. And also the time-varying electric and magnetic field propagate as a wave governed by the wave equation. So I show you the wave equations for electric field and also magnetic field. But if you are dealing with the time harmonic field, then you can reduce the wave equation into Helmholtz equation. And in this expression, there's no time variable, so the calculation can be particularly simple. So this is a few key points I want to tell you in this session. Thank you.